Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, what I want to teach you is how to use, and we'll again be using ode45, which is the basic Runge-Kutta technique out of MATLAB, and we're going to do this for systems of equations and for higher order differential equations. So first, I've set up this little system of equations here where y prime equals x or y2 and x prime equals negative y. And I set it up as an m function because frankly that's going to be your easiest way when you have anything other than a very simple first order differential equation. So I created my script over here. I've saved it as tofunc, and I now want to try to solve this. So the approach is going to be that I want to do the ode45 just like we were doing in the previous lessons, okay? But now then my function is going to be this tofunc, and so the way I'm going to refer to that is using the at, and that way it will go over and find that. And then I want to put in my initial values, so when t is -1, y is 1. And my starting values, I want to do them when both x and y are 1. Okay. I'll just let it do the graph. That's fine. And I'll bring that over. And we see that, you know, the behavior of these two graphs that we get. You can, obviously change your functions over here to whatever you want to, but it solved a system of equations, and I got two very different graphs as a result of that. And I could have written them to a file, okay? So it would be going to t and y, but I would have y1s and y2s, okay? Now, if you wanted to do a higher order differential equation, what you do is you basically take the derivative and set it equal to a variable. So in this case, I have y prime prime. If you look at this line right here, y prime prime plus y prime equals y plus t. So what I'm going to do is I'm going to say, okay, well, if I name z y, or name y prime z, then this is z prime. So z prime is equal to z, y, and t. And so I write this as a system of equations up here. When I translate that into the notation that is helpful for MATLAB, I end up with dy dt for the first variable is y2. dy dt for the second variable is y1 plus t minus dy dt of 1. Okay, so we're playing a lot of translation games here. But y1 is y, y2 is z, which is y prime. Okay, so check and make sure that that makes sense to you. And so now then what I want to do is come over, and again I'm going to use this same ode45. So ode45 at, let's see, I named this one second order. Okay, and then I need to put in my initial values. So again, we'll just go with -1 and 1. And this time we want to start them at the origin. And we're just going to have it output to a graph again. But now you see our two variables there, okay? And it also has given me an output of what those various, the first derivative and the second derivative at each point. Okay, so that concludes this video lesson for using the basic Runge-Kutta method using MATLAB for systems of equations or higher order differential equations. Thank you very much for your time.